Hello everyone. In this session, let me continue a few concepts regarding digraph. You are already familiar with digraph. I have already done the same concept in the previous session. A graph which is directed, or else I can say a graph in which each edge is mentioned a direction. Right? Suppose I have considered a graph something like this. Since I have clearly mentioned the directions for all the edges, so this is a directed graph. Now next concept is Indegree and outdegree. Indegree and outdegree. So as the name itself indicate, I have explained the same concept while doing the graph theory also, but again you have the same concept in discrete maths also. Now hope it is clear. Let me repeat once again. Digraph is a graph in which each edge is given a direction. Fine. Now, in degree of a vertex V. In degree, we can discuss for any vertex in a graph. In degree is none other than number of edges or number of what we say arcs. Edges is same as arcs. Number of edges are arcs which is directing, or else I can say which is entering to the particular node is its in degree. I'm repeating once again. I'll give you simple example. See here. Suppose if I'm going to consider a vertex D. For vertex D, the number of edges directed or number of edges which is entering to this point is only 1 given by this edge. Right? So in degree of this particular vertex D is 1. Similarly, in degree of this E is 1. Now coming to in degree of A, do we have any edges which is getting inside the vertex A? We don't have. So in degree of this vertex A is 0. Clear? Similarly, out degree of vertex V is number of edges coming out of that particular vertex. Now see here, vertex E, number of vertex coming out is only 1. So out degree of E is 1. Fine. Again, out degree of A is 2. Why? Because number of vertex coming out from A is 2. I'll give you one more example. Suppose if I have a graph, say you have to look at the directions. It is very important to look at its directions. Right? I have considered a graph which is having 3 vertex and something like this. Now let me list a vertex here A, B, C, D, and I'll list in degree here and out degree here. Fine. Coming to the vertex A, number of in degree is clearly 1. Why? Because only one directed edge is getting into vertex A. So for vertex A, in degree is 1. Fine. And coming to the out degree of vertex A, how many edges getting out of A is only 1. So out degree is 1. Now coming to the vertex B, in degree is how many vertex? See 1. In degree we have to count, right? So 1. Again a self loop. Remember, self loop has to be taken as both in degree and out degree. Key point is that self loop is both in degree and out degree. You have to count that as both in degree and out degree. So when you counting in degree of B, 1, 2, 3. See here, 1, self loop 2, again from this 3. So in degree is 3. Coming to the point of out degree, 1, 2. Self loop is considered as both in degree and out degree. So 1, 2. Clear? Now coming to the vertex C, in degree is only 1. Fine. Coming to the concept of out degree, 1, 2. Clear? Now for vertex D, we don't have any self loop. Look at the direction of D. In degree is 1, 2. Out degree, do we have any out degree vertex from D? Yes, we have. See here. So 1. Clear? So in degree is number of vertex entering into the particular vertex. Out degree is number of number of edges coming out of the particular vertex is called as its out degree. Now the path and the path, cycle, length, I hope so you remember all this concept. Length, path, cycle. When do we say path? In a graph we can obtain a path. It is sequence of or a collection of vertices. Right? Now initial vertex and terminal vertex is same, then that path is called as cycle. I have given you n number of example. Hope you remember the same concepts. So there is a chances to ask the same definition in discrete maths as well. But the key point here is self loop is considered as both in degree and out degree vertex. Fine. Now coming to the path. It is just the same concept as we done in graph theory. Anyhow, I'll give you one simple example in order to convey the meaning of path. Fine. Let me consider one single graph with vertex, say 5 vertex I have. 4, 5. So it is a digraph clearly. Why? Because I have given a direction for each of the vertex. So only for vertex 1 I have a self loop. So this is what I have a graph, right? Now since we are in the further topic, we have a concept called connectivity relation. In that case you have to know the meaning of path. So that is why I am giving you an example. Path is none other than a length of an edges. That is maximum number of edges, or I can say maximum length in a given graph is called as path. I'll give you one example with reference to this particular graph. Suppose if I'm going to consider 1, 2, there exists a relation from 1 to 2. Why? Because both are connected, right? So this is of path of length, which is, what is the length of this path is 1. Here we are not going to take any in degree or out degree. Remember, we are just counting the length, that is number of edges. See? Here 1 to 2 is a path of length 1. Fine. Now if you are going to consider 1 to 1, it is a self loop, right? So it is a path of length 1. Similarly, if I am going to take 1 to 4, path of length, see here 1 to 4, the only way I can reach is, you have to look at the direction. 1, from 1 to 2 I can go 1, 2, 3. So I have reached 4. I started with 1, I have reached 2, again I have reached 3, again from 3 I have reached 4. So 1, 2, 3. So 1 to 4 is a path of length 3. Similarly, 1 to 3. If I am going to consider 1 to 3, it is a path of length 1, 2. Clear? Path is none other than, it is just a maximum length for reaching vertex 1 to vertex last, or else I can say it is a maximum length that is taken to reach from initial vertex to a final vertex. This is what the path concept is. Next is connectivity relation. Connectivity relation. Generally it is represented by R infinity. Fine. And you'll be getting one theorem based on this concept. Before getting to the theorem, let me make clear this concept, connectivity relation. It is given by R infinity. It is just simple. Suppose if we have an ordered pair x comma y in a relation R, meaning is that I have an element x and y in a relation, then there is a chances that there exist n number of elements in between x and y. That is, except x and y, all these vertex I am explaining with reference to digraph. Fine. Suppose x and y is in a relation R, that is an ordered pair. In between x and y, except the endpoints, there is a case that there may exist n number of vertices in particular digraph. Then those elements are, we can say those vertex should be connected. Meaning is x1, x2 should be in R, x2, x3 should be in R. So if you continue the same process, let me take an n vertex xn, previous term is xn minus 1. So that should belongs to R. So this is what the meaning of connectivity relation. So I can write connectivity relation R infinity as R union, R square union, R cube union, so on, union R power of n. In the sense, if I have n number of elements in between x and y, all those elements should be related to each other. So collection of all those elements is called as connectivity relation, and it is represented by R power of infinity. So the moment when I write R power of infinity, it represents connectivity relation. So I'll give you one example in order to convey the same connectivity relation. Suppose, let me take the same graph. Fine. So I'll name this vertex in order to remember. Let me take this vertex as A, B, or else let me write one more time so that you will understand well. So here I have a graph, say vertex A, vertex B, and vertex B to C, again vertex C to D and vertex D to C. And obviously I have to consider digraph, so I am giving directions to this particular graph. Fine. Yeah, I have given direction for all the existing edges. Now what I am going to explain is connectivity relation. I have to form a connectivity relation. Now before going to write R infinity, let me make a note of a path which is of length 1. So path of length 1 I have to list. Look at the relation A to A. You have to make a list of all the ordered pairs which is of length 1. Now from A to A is length 1. So I can write A comma A. Again from A to B is a path of length 1. So I have to write A to B. Again look at the length B to C. B to C is a path of length 1. So I have to add B to C. Again C to D. Again D to C. C to D, since I have already written C to D, we don't have C here. While writing also it is very important to take care of direction. C to D, there is a relation, so I have written C to D. This is E. Now we cannot write D to C. Why? Because we don't have this direction arrow. Fine, we have direction only in this way. So C to D I have written. Again D to E is a path of length 1. Again, do we have relation from E to C? We don't have. But anyhow we have from C to E. So I have to write C to E. So is there any possibility to have length of a path 1? We don't have. So only these 6 are the cases which is of path length 1. Fine. So A to E is a path of length 1. A to B is also one of length 1. B to C is 1. C to D 1. D to E 1. Again C to E 1. Now let me make a list of path which is of length 2. So I am listing the path of length 2. Let me write here once again. Let me take this as R1, R2. So when I write R power of n like R1, path of length 1, R2 represents path of length 2, R3 represents path of length 3. Now I am listing path of length 2 is, see here, I can travel from A to B, B to C. So A to C is path of length 2. Again, I can reach from B to C and C to D. I can write B to D is path of length 2. Fine. Again, C to E. See here. C to E is path of length 1. I have already written. Again C to D, D to E I can travel. Right. C to D 1, D to E 1. So path of length 2. Again I can write C to E here. Fine. Again, do we have any possibility? Yeah, I have C here. B to C, C to E. Fine. B to C, C to E. So I can write BE. So these are a path of length 2. Do we have any possibility? Definitely we don't have. If you want, you can check here. So A to C, 1, 2, path of length 2. B to D, 1, 2, path of length 2. C to E, 1, 2. Again B to E, 1, 2. So we don't have any other choice to reach a path of length 2. Now let me note a path which is of length 3. So it is represented by R power of 3. Clearly I can write A to D is a path of length 3, right? 1, 2, 3. So A to D is path of length 3. Again 1, 2, 3. I am reaching B to C, C to D, D to E. So it is a path of length 3. So B to E I can write. Fine. Again one more possibility is there. 1, 2, 3. So A to E, 1, 2, 3. A to E I can write. So this is a path of length 3. Apart from this, we cannot have any choice. So this is the only way to write path of length 3, path of length 2, path of length 1. Again, do we have any path? Do we have, next let me check for path of length 4. Do we have any path of length 4? Yeah, I have C here. 1, 2, 3, 4. In the sense, I am starting with vertex A, 1, 2, 3, 4. So A to E is a path of length 4. Do we have any other possibility to get path of length 4? 1, I have already written 1, 2, 3. 1, 2, 3. Rest of the less than 4. So only path which is of length 4 is A to E. So we don't have any path of length 5. This is the maximum path which is of length 4. Fine. Now I have stopped here. So R1, R2, R3, R4. Now your connectivity relation R infinity will be collection of all these relations, in the sense collection of all these paths. So I can write this as A comma B. I'm listing this B comma C, C comma D, D comma E, without repeating I have to write C comma E. Again A to C, do we have A to C? We don't have, so I am writing it A to C. B to D, we don't have, again I am writing that. C to E, I have already written, so I am not going to write it. B to E, no, so I am going to write it again. A to D, no, I don't have, so let me write A to D. Again B to E, no, I don't have, so let me write that. A to E is also not there, so I have written this. Fine. So A to E already there, so let me stop here. So I am going to list all those length of a paths, that is all those ordered pair which is in the relation. So I have combined, or else I can say I have taken union of all the R1, R2, R3 existing paths. I have taken union of all the existing path, that will gives us a connectivity relation. So it is represented by R infinity. Hope it is clear for you. Now we have a theorem based on this connectivity relation, and we have to prove that R infinity is equal to R power of 1, R2, R3, so on, union R power of n. Anyhow, I have convinced already this theorem through this counter example, but we have a wording proof for this particular theorem. But before going to that, you have to know one of the concepts, say magnitude of A is equal to n. So remember, whenever I use this symbol magnitude of A, that will represent cardinality. Cardinality, meaning of cardinality is, suppose if A is any set, cardinality is none other than number of elements present in that set A. Suppose if A is equal to, say I have an element something like this, then cardinality of A is equal to 1, 2, 3, 4. So number of elements present in this particular set is called as cardinality of a given set. So hope this connectivity relation is clear. Now let me prove this theorem in the next session. I will send you the notes, and one more thing I forgot to tell you, that just now I have explained the concept, no, that is finding the paths in a particular graph and finding indegree and outdegree, something like this. I will send you solved example problems in the notes, so please go through the example problems and copy the same in the notes. If you are finding any doubts in that particular notes, you can free to ask. Thank you. Continue in the next session.